Greetings. This is the review for the second midterm. Same as the first midterm, it's 8 to 8:30 on Monday and Wednesday and Friday during class time and online. Answers are submitted on Canvas and it will be in week 10 on your syllabus. As before, if you have problems getting the stuff submitted on Canvas, if there's an emergency only, I guess I should stress, then scan it and send it, and then we'll decide exactly what to do with it. So it's not meant to penalize you for problems that you have, but it's also not meant to allow kind of routine overstepping of the timing of the test as well. So we'll decide what we want to do with it once we get it. The material covered is in the second stage of the class. We cover fluid dynamics, which is Bernoulli equation for weeks 4 and 5, except for the acceleration part as 4.1. We talk about control volumes for conservation of mass. We talk about conservation of momentum in week 7, and that's it. Individually, the 3 questions on the Monday, Wednesday, and Friday. The first one deals with Bernoulli. Has a free jet component in it, and you also need to recall manometry from the earlier part of our course. The second one uses Bernoulli, is concentrated on conservation of linear momentum. The best one to review would probably be week 7.2, when we talk specifically about static, steady, and moving control volumes for linear momentum. And the third one is again Bernoulli, but rotational momentum equations. The material you need to know in brief, I guess, is to know what Bernoulli is. You know that Bernoulli is written between one location to a second location. For all of these applications, it doesn't matter which is upstream or downstream. This is the expression that sums pressure, elevation, and velocity head. I guess there's a squared on that term as well. If we only know 4 of these parameters, then we can close the system of equations by using conservation of mass that just says that the mass rate in, or the volume rate in, or the mass rate in is equal to the mass rate out. Nothing more involved than that. If we want to, for particular geometries, we can calculate the equation for a free jet just by writing the equations for a velocity on the surface and a velocity at an exiting free jet. If we do that, we get this particular expression. The assumption usually is it's a big tank, and therefore the velocity on the surface is equal to 0, in which case we end up with this single expression. And we also need to be cognizant, I suppose, of relative frames of reference. And the relative frames of reference mean that if we view from a static location, our static view of what's going on is equal to the velocity of a control volume plus the vector sum of fluid velocity coming out of that moving control volume. So that the addition of these 2 velocities is equal to what a static bystander sees, and that is represented by this expression here. Dealt with in the earlier part of our course, we talked about manometer rules in going up and down through fluids. If we go down through a fluid, we add fluid pressures. If we go up through a fluid, we subtract fluid pressures. If we go across a fluid between 2 locations that are the same elevation but are simply connected, then the pressure doesn't change. And if we look at the pressure change in an evacuated area, pressure change in a gas, the unit weight is so small, maybe 1,000th of the density or unit weight of a fluid, then we can ignore typically the unit weight of the fluid. And if we're in an evacuated portion of the system, then the pressure that we should use should be the vapor pressure. If we're looking at conservation of mass, which we dealt with in week 6, then we can look at the behavior in terms of a control surface that surrounds a control volume. We can look at fluids entering into that volume and leaving that volume. We define the conservation of mass by this simple equation. The steady state portion is that the sum of mass flow rates is equal to 0. Mass flow rate is equal to the density times the area times the velocity across the surface, the relative velocity of the fluid across the surface. The terms together are the mass flow rate, so it's in kilograms per second, but we can also look at the volumetric flow rate, which would just be the product of area times velocity, which we've often called Q. We need to be cognizant of the sign convention. The sign convention always is if the fluid is flowing out from the system, because it's aligned in the direction of the normal to that boundary, then it's a positive value of this velocity. If the fluid is going into the control volume, because it's in the opposite direction of the normal to the boundary, then that value is negative. So this term here represents the steady state behavior. Mass rate in equals mass rate out. If there's accumulation terms, they're represented by these two components. This component is a rate of change of density in a controlled volume. So this would be what we'd call our tire. So if you're putting air into a tire, the density changes, but the volume of the tire doesn't change. And the opposite is that the density stays constant and the volume increases. And so the second condition would be where, for instance, we're filling a volume and the height of the fluid free surface rises as a function of time, and as a result of that, the volume is changing as a function of time. Again, we have to define a sign convention for this, just like these flow rates in or out. And the sign convention is that density or volume increasing with time gives us a positive quantity. So this has to be cognizant of that full sign convention. If we take it the next step and look at conservation of linear momentum, we can do the same things. We look at flows into a control volume. We only looked at a control volume which wasn't deforming, and so it translates at a volume of the control surface, which is constant for every single point around this control surface, right? The velocity here is going to be the same as the velocity here, merely because it's translating at this velocity. And the expression that defines that behavior is that the sum of the forces is equal to the velocities times by the mass rate of flow, all summed for all of the boundaries that are present. The mass rate of flow is the same as it was before, the flow velocity relative to the boundary, with the appropriate sign conventions for the mass flow rates, as we looked at here. These same sign conventions here. And so that conforms to this. And then multiplying this is the velocity in a Cartesian direction. So this velocity here is in the positive direction of the x direction, which is towards the right, and therefore this magnitude would be positive. And this one is positive in the z direction going up, and this would be positive. If there was a fluid flow going out of here, which would be V3, then that would also be positive and in the x direction, because it's in the positive x direction. Can't see it here because it's off screen, but our sign convention is always that the z direction is positive upwards, hence this value here. This is a vector equation. There are three values of forces, x, y, and z, three values of velocities, x, y, and z, and one summation of mass flow rates, just like you see here. Typically, we take one of them because we only deal with one at a time. So if we resolve in the x direction, we have this one equation here, which looks at forces in the x direction and velocities in the x direction. And because this is an inertial reference frame, this velocity is a static velocity in the x direction. And so when we use the static velocity, we can replace it by each of these two components here. The velocity of the control surface and the fluid velocity across the boundaries. And we can write this equation as this. So this expression and this expression here are exactly the same expression. All we've done is we've just substituted for this. And our reason for doing that is it allows us to be able to solve problems both for static behavior and for moving behavior. And so we can look at each of those cases. We did an example with the jet lev. That is a static problem in that the velocity of the control surface is equal to 0. And if this is equal to 0, then that is equal to 0. And the equations simplify. The other thing that we can do is to realize that the product of the velocity of the control surface and the mass flow rate, because this is just a single number for any problem, and this is a summation on all the boundaries, we know that for a steady problem, the sum of the mass flow rates are equal to 0. And so since this is a constant and this is a summation equal to 0, then together these terms must equal 0. So we can drop this term completely. So for steady problems, we can reduce it to this behavior, which is the velocity across the boundary multiplied through by the mass flow rate, sum to each other. And so we can use that to do two behaviors. We can set the forces equal to 0 and calculate what the velocity is, because we know that we can split this term here into magnitudes which are equal to, if we just use this expression here, where is it? We can just rewrite this in terms of the velocity W. So this would go to W is equal to static velocity minus the velocity of the control surface. So we can substitute this value in for this magnitude here. And if we do that, we are able to solve for these two conditions. We can solve for when the sum of the forces are equal to 0. Then we can use that to define what the velocity of the system is. And we can also use it when the velocity of the control surface is equal to 0. And we can use this summation of this term, V static minus VCS. This is the static jet velocity. This is the velocity of the control surface. If this is equal to 0, then this is just equal to the magnitude of the impinging jet. If we want the force equal to 0, then these two magnitudes have to be equivalent to each other. And so we can immediately tell the magnitude of the velocity of the vane. So those are the two end-member conditions. If we deal with unsteady conditions, so the gas cylinder case, so this was the jet lev and also the moving vane were the two ones that we talked about here, static and steady. The unsteady condition, we have to include this term now. And I guess the rationale is that the velocity of the control surface is constant, but now the sum of the mass flow rates are not equal to 0 because it's not a steady problem anymore. So if you think about it, more mass is coming out than is remaining. So the mass in here must be depleting as a function of time. And so this is not true. And so we can't throw away with this term. So we use this form of the equation to solve for this problem. And again, we can solve for the magnitudes of these two cases. We can either put the force equal to 0 and solve for the velocity, or we can put the velocity of the control surface equal to 0 and solve for the force that we have to apply. We talked briefly about the idea of work or energy, or power, I suppose. And we note that power is equal to force times displacement over time. So this is really a velocity. So force times velocity is power. The units are watts or joules per second. And so what we can do is for these two end-member conditions that we talked about, either holding the vane static and calculating what the force that's applied, which would give us 0 velocity of the control surface and a maximum force, or releasing the vane and calculating what the velocity is, which would give us 0 force, but a large magnitude. For each of these, multiplying the force, which is 0, by the velocity, gives us a power which is equal to 0. Also, multiplying a velocity by a large force would also give us a power equal to 0. So the product of the force times the velocity gives us 0 power here, 0 power here, but at some intermediate point where there's a finite force and where there's a finite velocity, the product of these two gives us a magnitude of the power which is non-zero. And that's it's not necessarily at the midpoint. It would be a curve that looks like this, but at some intermediate magnitude of force and velocity, we expect to have the maximum power. The final version is to look at rotational momentum, or angular momentum. And we made the point that the behavior is just like a translating vane, but it's on a lever arm. We made the point that we could use the force equation, which is, or the linear equation, which links force to a velocity times a mass flow rate, just as we had in this expression here, if you like. But what we can do is we can just multiply that expression by the radius arm and the radius arm on both sides. And then this term here becomes what we will refer to as a torque, force times the radius. And we have our moment of momentum equation. So this is our torque. This is a radius multiplied by the other components. This is still a density, area times a velocity out of the control surface. And the only other things that we have to remember are that we can define the velocity of the control surface. We have to choose a sign convention, and if this is positive for this sign convention, then that's important because it decides the positive rotation velocity for this rotational velocity omega. So VCS would be positive omega as well. The velocity that we travel at, v theta, is equal to the product of the radius, the arm that it goes through, multiplied by the rotational speed. And this would be in radians per second, which is 1 over seconds. Radians are dimensionless. And we know that 2 pi radians per second is equal to 1 revolution per second for the conversions. So it's important to be able to link this velocity to the rotational velocity, etc. Again, we can solve the problem, again, for the fluid coming out of the vein. We have two end-member conditions. We can either let the vein rotate, in which case the force that we apply to the vein, which is positive in the same direction as this velocity, that's our positive coordinate direction here. So if the force is 0, then from solving this equation, this will be going at a maximum velocity, which is typically equal to the negative right? When these are negative of each other, this will be a force that's 0, or a torque that's 0. And of course that makes sense that if the water is coming out in this direction, you'd expect the velocity of the vein to be going in the negative CS direction. So one condition is where we release the vein, in which it can rotate. The second one is where we hold the vein static, in which we get the maximum torque on it. And we can go through the same exercises before. We could multiply force by a radius, and this becomes torque. We can multiply, we don't have to multiply VCS by anything, but if we look at the product of torque multiplied by VCS, if that's right. No, sorry. Let me change that. Torque multiplied by rotation. We know that rotation is equal to V theta R, V theta over R. And so we can rewrite this as torque equals force times R times V theta over R. So in which case we lose this, and we end up with this being power, this being power. Then we end up with power being equal to force times V theta. So it's the same. So these two expressions that we show here is that power is equal to the torque multiplied by the rotational velocity, or the force multiplied by the VCS. They both give us Newton meters per second, which is a joule per second, which is equal to a watt. So that's it. I don't have anything else to say. So anyway, happy hunting in week 10, and good luck.